variables they are created to allow for quantitative effects in a regression model. So the variable is not the real number, it's not the data that we collect, but it is a variable that we create. Okay, that variable that we create to present different effects of different categories. The W variable we take the value 1 or 0 according to whether or not the conditions present or absent for a particular observation. So if the condition is present, then we assign 1. So we create variable. So just one variable, and the variable not only one variable, but variable that consists of only two values, 1 or 0. So if the condition is present, let's say you want to present the effect of different gender, so we have male and female. So now the condition is whether the observation belong to female, for example, to be considered an example. So we assign 1 if the data belong, the observation belong to female, if we assign 0 if not. Okay. So for example, suppose we are investigating the relationship between savings and income. So our initial model is given here. So our dependent variable saving, and then we have income y to explain the saving. So however, we are concerned that female saving may be below that of male individual. So let's say we have data, a group set of data, and then some of them belong to male, some of them belong to female data, so collected through survey, for example. So there is possible that the way that male and female behave in terms of saving different, so it's not necessarily the same. So one way, one option we have is just to consider they behave the same. So we have data for male and female, then we can just combine all data. So we do not take into account that observation belong to different gender. So we just consider or assume the way that male and female save their money just the same. So we just combine. Again, that one option. So however, we are concerned that female saving may be below that of male individual with income. To test for this, we can introduce a dummy variable to distinguish between the observation for male and female individual in the relation. So another possible way is, if we believe that the way that male and female save their money not the same, different, so we have to include that in the model. Okay, so one possible way to by adding or by having dummy variable, that we use dummy variable, and we use that dummy variable to present the effect of different gender. Okay. So suppose we are estimating saving equation for male. One method is to restrict our. So there are what we call that just now I mentioned to you that there's one way we just make assumption that both male and female behave the same, but if we believe they are not behave the same, they are different, the way that they save their money is different, then one possible way is to split. So split data into two groups. So one data only for male, data for male, and then another group of data for female only, and then we estimate two separate models. That's another one alternative way by estimating regression model separately for male and then another one for female. However, restricting our sample to a single subpopulation, in this example, male individual does not facilitate comparing different groups. So it does not allow us to perform hypothesis testing in order to identify or to say that there is significant difference between the two groups. Although we can estimate the two different models for different groups, but by doing so, it does not allow us to perform hypothesis testing in order for us to say whether there is a significant difference between the two groups. Okay, so that's one of the problems. So alternatively, we can just create just new one model, but we include that variable. So what if we wanted to know whether women save the same as men controlling for income? What if we wanted to know whether an additional RM1 in income had the same effect on saving for women as for men? So this one, the first one in terms of intercept, whether we want to know whether the intercept for the two groups the same or not. So this one in terms of the second one, if in terms of slope, whether Does it look remain the same for the two group or not? So suppose we have a sample of individual. We want to know whether women save the same as men contributing for income. So we can create a variable. So we can use different whatever name lah. So we can, for example, T to represent that variable that equals 1 if an individual is female, 0 if an individual is female. So I don't basically for gender we have two groups. We have two categories, two groups, male and female. So we can create up to two dummy variable, one dummy variable for male, one dummy variable for female. But if we have a normal intercept beta 0 in the model, then you cannot include, later explain more detail lah, you cannot include dummy variable for all categories. Otherwise we have a problem of perfect collinearity. So let's say, for example, like data, we have this one, the same data, same data. So we have saving as income Y, and then we have a variable representing whether it is the observation belongs for female or male. So you need to create a variable. So in this case, let's say you create a variable for female, for example, or male, and you need to assign. So let's say you create a variable. You can use whatever name lah. Let's say we need as male, so that we variable for male, and then we need, if the condition, meaning that if the observation belongs to male, we assign 1, if not we assign 0. So for example, this one, the first observation belongs to female, then we assign 0, and then the second observation belongs to male, we assign 1, and then and so on lah. So this one 0, 0, and so on. Okay, and then we can do the same for female as well. So meaning that we have two categories, male and female, so we can create up to 2. But again, if we have the normal is set constant, then we can include all in the model. So this one, alternatively, you can use, if you have data in Excel like this, you can use function to create that variable. You can use if function. So you can put if. So if this cell equal to F, sorry, this one M, that we have to make first. And it is equal to 1, if not equal to 0. So this one way, instead of you assigning 1 by 1, which is time consuming, you have last sample size 1000 observation, then you're going to spend a lot of time to assign 1 by 1, either 1 or 0. So you have data, if you have data in Excel like this, then you can use a function. So you put that if that the value in that column equal to 1, and then you assign 1, if not you assign 0. So it's 1, 0. So if equal to M, 1, if not equal to M, 0. Okay. So if you drag this down, then you have the dummy variable. So this is what we call dummy variable. Okay. Equal variable. So either there are only two options, there are only two values, 0 or 1. And at the same time, you also can have dummy variable for female. So female means that if the observation belongs to female, we assign 1, if not we assign 0. So this one, male, okay. So this one, F, female, and then we put 1, if not 0. So in if we are not able to assign values we are unable to ask if used to simply assign 1 or 0 for categorical variable in mistaken. So one way to create a variable, you can do that in Excel, for example, like this. Okay. And then you transfer the data. You transfer the data into the use. So if you want to create a variable for female, and then that is not. So the first observation belongs to female, to be someone. If not 0. Okay. So now, as mentioned before, we have different option. First option, we just ignore the fact that our data belong to different categories, male and female. We just assume all behave the same. So we just estimate model without taking into account male and female. So we just estimate the model and obtain this output lah. So the data given here, we have two. Data edition 9, this one. If this one, the data for all observation. Okay, and then we have D1. So in if you cannot use D. This one is up to you. You can use whatever name you want to for the dummy variable, but you can use D for differencing. D for use for difference. So you cannot. So here I put D1 instead of D, because D cannot be used for other, because it is reserved for differencing. Okay. So just now we have our saving data, income data, and then dummy variable. This one dummy variable for female, not for male. This one dummy variable for female. So we cannot include both. I mentioned just now you can create dummy variable for all, but when you estimate model, if you include C constant in the model, then you cannot include dummy variable for all. Okay, later we'll explain why. So this one, the first option, we just estimate the model without taking into account that observation belong to different categories. We just assume they behave the same, so we estimate as usual lah. So we have S space C space Y. So we have these. So this one, if you assume male and female behave the same in terms of the way that they save the money. So meaning that in terms of integration, we say that for every 1 ringgit, of their income, 1 ringgit additional increase in their income, each of them will save about 10 cents. Okay, around 10 cents of that income, every 1 ringgit they save for. They allocate for saving. Okay. So without taking into account that, meaning that here we just assume that male and female behave the same. Okay. But here, if we believe that male and female behave differently, and then we should just now whether we estimate the model separately or a better way is that we just add dummy variable. So what happens if we estimate the model separately? So let's say you have to split data into two now. So this one I just sort data, male first and then followed by female. So we have the data given here, data sorted values. So this one, the first 21 observation for male. Let me check. So this one 0. The first 21 observation for male and the rest for female. Okay. So using the second data set, you can estimate models separately for male and female. So if you do that, you go to quick estimate equation. So we have S space C space Y for male first, observation number 1 to observation number 21. And then you compare, you see the difference. So meaning that we get different estimate. If we estimate the model separately, you can see the estimate are not the same. The salute parameter, if for the case for male, this one for male, so 0.06. So meaning for everyone. Just now when we estimate models together, it says that and for every 1 ringgit 10 cent goes to saving. But now for if we just estimate for male only, and it says that about 7 cent. So every 1 ringgit 7 cent goes for saving. And then how about for female? So we estimate another model for female. So we have S space Y space Y. We have data from 22 to 49. Okay, so just name the first one equation 1. So if we estimate you for the case of female only, so we have for every 1 ringgit 14 cent goes to saving, goes to saving. So you see the difference. So meaning that it shows the need for us to consider the fact that different gender behave differently. So we can assume they behave the same in the way, in terms of the way that they save their money. But although here we can get estimate using separate models, the problem is as I mentioned just now, that we are not able to perform health testing in order to see the significance of the difference between the two groups, male and female. So in order to do that, we have okay, that is by having dummy variable in the model. So we go back to the earlier data set, not the second one, the first data set. Use second set also can, also can get the result. Okay, this one, just now I explained to you that this is dummy variable, but this one dummy variable for female, not for male. Dummy variable for female. So we can estimate model and add another variable, that is the dummy variable E1. Okay, so we get this one. So how to interpret this one? So how we are using this model enable us to have estimated model for male and female. So you have to look at this the next slide. So this is our model. So we have dependent variable saving, and then we have intercept, and then we have our independent variable income, and then we add dummy variable, and the dummy variable here represent dummy variable for female. So 1 equal to it is equal 1 if the data belongs to female, and then it is 0 if not. If not means that male. Yeah. So you see, for the case of male, D equal to 0. Okay, for the case of male, D equal to 0. So our model reduced to be this one, beta 0 plus beta 1. Why? Without this one, because this one is 0 already. Okay. So B1 represent, the beta 0 represent the saving when income equal to 0. So saving when income equal to 0 for the case of male. And then for the case of female, D equal to 1. Okay. Dummy variable equal to 1. So we have this. So meaning that you can rearrange this one. So your intercept now beta 0 plus beta 2. Beta 0 plus beta 2. So for the case of male, intercept beta 0 only, because this one 0. For the case of female, intercept beta 0 plus beta 2. The slope parameters are the same for both categories, male and female, if you use this model. Okay, but later we will consider a model that allows the intercept to be different, that allows the slope to be different as well. So in terms of graphical representation of the model, so this is the model for male. So intercept means that the salary, the saving when income equal to 0, the saving for male is given equal to beta 0. Okay, as this one the slope, meaning that for every one increase in income, male will save beta 1 out of the 1 ringgit. Okay, beta 1 represent every 1 ringgit how much goes to saving for the case of male. Okay, but for this model consider the slope to be the same for male and female. This model only allows intercept to be different for male, for the two categories. Okay, only the intercept, but the slope we consider to be the same. Okay, so we consider both male and female for every additional 1 ringgit the same amount, but only what we call that when y equal to 0, when income equal to 0, so we have to allow them to have different. Okay, so meaning that the level of saving to be different. So beta 2 is the difference in the intercept between male and female. So just now is the result we obtained just now. In order to know the value of intercept for female, you have to count, you have to calculate. Okay, estimate for beta 0 plus estimate for beta 2. So beta 2 is given by this. Beta 2 is the coefficient for D. Okay, beta 2 coefficient for D, dummy variable. So we have slope to be the same. Slope for both male and female 0.10, meaning that for every 1 ringgit increase in income, 10 cents goes to saving. But when income equal to 0, saving, the what we call the basic saving. Okay, when income equal to 0, for the case of female, they are saving negative 14 ringgit. So meaning that negative, so negative. So they don't have income, but they have oh sorry, this one for female, this one for male, for female, this one plus this. Okay, you have to have this one for female, this one for male. Okay. So negative means they don't have savings, so maybe they have a debt or they own some money to other person. Okay, when the income equal to 0. So this one, so in terms of interpretation, for the case of beta 1, holding other internal variable constant and increase N1 income increases the pre-tax saving by about 10 cents. And then for beta 2, holding other internal variable constant, if we take men and women with the same level of income, female save 1.17 more than male. So because beta 2 represents additional as compared to male, how much more female save as compared to male. Okay. So if you use the model, if you consider it is correct, of course you have to, before you in actual practice, you have to check for all the assumption, the autocorrelation. This one not really autocorrelation because autocorrelation only happen for the case of time series data. So this one is not time series. This one cross sectional. So although W-Wilson value is not that, it's not the correct representation of the influence of past observation, because this is the cross sectional. So cross sectional, once you change the order, you get different value of W-Wilson. Okay, so basically the autocorrelation problem happen for time series data. Normally it's happen for time series. It's not time series data. It's a cross sectional. So you have to understand the difference between cross sectional and time series. Time series data, whether you have annual data, monthly data, quarterly data, that one time series. Okay, this one the data collected at the same time from different source. So we have 49 different individuals. So we have the information about the saving, information about the income. So this is cross sectional. So just now we have different set of model. So different set of data. If you change the order, you get different W-Wilson. So for example, if you use the second data set as now, if you estimate using all data, so we get 0.87. But if you use the first observation before we sort the data, so you said 0.5, 0.51. But when you change the order, you sort male first and then followed by female, we estimate the model, we get 0.7. So meaning that the reversion is not correct. It's not valid for the case of cross-sectional. So cross-sectional, we can change the order. Time to data, you cannot change the order because, for example, N1 data, you cannot put the data, you cannot change the order. You cannot put the first observation to be the second because it is in order. Okay, time series. But this one cross-sectional, you can change the order. Once you change the order, you get different reversion. Okay. So again, autocorrection is not really a problem when we have for the case of cross-sectional data. It is a problem for the time data because the previous observation influenced the current observation. So this one again, but again for this one, if let's say assuming that this model is valid for us to perform hypothesis testing, then how to perform hypothesis testing? Then you can perform hypothesis testing as usual. So what t-test could be run to test hypothesis that men and women have the same saving for the income constant. So in this specification, the expected saving for men and women differ only by beta 2. So you need to test. So here we want, after we estimate, we want to know whether there is significant difference between in terms of saving for male and female. So we test this one. Okay, so because if this is not equal to this one is not equal to 0, then there is difference. If it's equal to 0, there is no significant difference. So we have to test whether beta 2 equal to 0 or not equal to 0. Okay. So you have to test this one, test that at beta 2 equal to 0, to test that expected saving are the same for both groups. So the coefficient on the dummy variable in the regression 1.17 with standard deviation 3 point something. If you calculate the t ratio, you get 0.38. You compare with the value from t table, so it is less than critical value, so do not reject. Or based on the ABS output, just now ABS output it is okay, this one. So this one, the coefficient for beta 2, the beta 2 will present estimate for beta 2. So this one we can just look at the p-value. So p-value 0.69, less than greater than 0.05, so we not reject. Okay. So instead of comparing the critical value to the test testing to critical value from table, you can just conclude based on p-value. So p-value 0.69 greater than 0.05, so greater than significant value level, so we do not reject. So conclude that beta 2 just equal to 0. We conclude that the true coefficient beta 2 equal to 0. So meaning that there is no significant difference between the saving for male and female if you use this model. So later we will get different result when we allow the intercept to be different as well. Okay. So there is no significant difference in saving behavior between male and female. Alright, so omitting a category. When we have a single dummy variable, we have information for both categories in the model. Thus, having both a dummy variable for male, female, and one for male is redundant. So you should not include lah. You should only include one because only by using one variable we are able to know whether the observation belongs to female or male. Because if 0 for let's say just now the example we use this one, then we run for female. So if value 1, then we know the observation belongs to female. If 0, then we know it belongs to male. So no need to include both. So no need to include dummy variable for all categories. Just here we have two categories, just include one. Okay. So as a result, we omit one category whose intercept is the model's intercept. So meaning that we exclude for this given just now they give the example of the estimate model, we exclude for male. So we only include dummy variable for female. So for the case, for the example that we considered just now, male is our reference category. Okay. So male when d equal to 0 is our reference category. Reference means that we refer the other category as compared to this one. So as compared to male, female has additional part of intercept equal to beta 2. So this is our male, our reference category. So we just include the variable for payment. Okay. So again, this omitted category is called a reference category. In the dichotomous case, the reference category is simply the category coded 0. For just now, the example just now, when for the case coded 0 male, so male is our reference category. When we have a series of dummies, you can see that the reference category is also omitted variable. So let's say you have another dummy variable. So let's say this dummy for gender. You have another dummy variable for additional, the highest education level, for example. So you have let's say you have 3 groups. So meaning that, okay, we take another example. Because they want to have 3 groups. Let's say we have another example whether they are working in government or private. Okay, government or private sector. For example, you have 2 groups. So whether all these respondents, whether they are working in the government sector or private. So you have 2 categories. So you can have another variable. So let's say D. So this one D1 and then D2 if they are working in the government sector, for example. Okay, so you create a variable just like what we did just now. You create a variable if they are working in government, if Y is not 0. Okay, so you can. So for the case we have more than 2 variables. So when both equal to 0, then that is our reference category. Okay, that's the. When all D equal to 0, then that is the reference category. Okay, when we have a series of dummies, you can see that the reference category is also the omitted variable. So multiple categories, we can use dummy variables to control for something with multiple categories. Okay, so just now I explained to you, I mentioned to you that if we have, let's say, we have another variable representing the highest education level. So let's say I have 3 categories. Let's say primary school, secondary school, tertiary education. So you have three groups, and then you can create a variable as well. But you can, because we have 3 categories, then although we can create 3 dummy variables, but when you estimate model, we just include 2. Okay, just include 2. You cannot include the variable for all categories. Understand that? So you can. We have, for example, we have highest education level for this 49 respondent. So we have 3 categories: primary, secondary, and tertiary university level. So we can create up to 3 data variables for each of the category. But when we include that in the model, normally we exclude 1. Okay, and that one, the one that we excluded, is going to be our reference category. Okay. So any categorical variable can be turned into a set variable because the base group reference category is represented by the intercept. So the intercept will represent the intercept for the reference category. If there are n categories, there should be n minus 1 dummy variable. If there are a lot of categories, it may make sense to group some together. Example, octal ranking 11. So let's say you have many categories. You have 100 categories. Then it's not a good practice that you include too many dummy variables because you remember your degree of freedom, sample size minus number of parameters. So you have too many variables, then you have low degree of freedom, which is will make your model, your estimate to be less reliable. Okay, so do not include too many variables, especially if it is representing different categories. So you have many categories, then what you can do is try to regroup. Instead of 100 categories, reduce it to have, for example, 4 or 5 categories only. Yeah, and then create that variable. Alright, so interaction term. So this allows us to have interaction between, so this interaction between dummy and independent variables in order to allow the model to have different, or in order to allow different group to have different slope as well. Okay. So the first example that we considered only allowed the intercept to be different. Right now we want the slope to be different as well. So in order to have that, you can introduce interaction between dummy variable and the independent variable. So when the research hypothesis state that the different categories may have different responses to other independent variable, we need to use interaction term. For example, gender and income interact with each other, so that the relationship between income and saving is different, stronger or weaker for male than females. To create an interaction term is easy. We just multiply the dummy and the independent variable. So for example, if we have just now, if we have the same variable, one for female, and then if for the case of male, we assign 0, so we have the dummy variable. So we just add the interaction between dummy variable and the independent variable, so that we have a different slope parameter for the income. Okay. So in this case, if for the case of male, then we have d equal to 0, this one also is 0, then we only have this one. Because this 0, this one 0, we only have this equation, this part equation for the case of male. So intercept for male, beta 0, and then slope for male, beta 1. Slope for the income, the slope parameter. Understand? The slope parameter is the coefficient in front of the independent variable. Okay. Intercept is the when y equal to 0, when all x equal to 0, then what's the value of y? That is our intercept. So for the case of male, when d equal to 0, so this one 0, this one 0, then we only have this one. So intercept beta 0 for male, the slope for male is beta 1. For the case of female, d equal to 1, this 1 equal to 1, so we have beta 2. This one equal to 1, so we have beta 3y. Understand? This one, if d equal to 1, so we have beta 3y. So for intercept, beta 0 plus beta 2. Beta 0 plus beta 2 is our intercept for female. And then slope is given by beta 1 plus beta 3. Okay, because we have beta 1y, beta 3y. Beta 1y and beta 3y, so we can combine both. We have beta 1 plus beta 3y. Okay, for the slope. So it is given by this. Okay, by this. You can see, if we include interaction term as well, then we allow the two groups to have not only to have different intercept, but to have different slope as well. Okay, slope as well. So in addition to that, we also can have interaction between dummy variables. So interaction between dummy variables is just like subdividing the group. So we have more, we can subdivide the observation into more different to higher number of groups. Okay. So let's say you have dummy variable for gender and then dummy variable for marital status. So we have. So this one for female and this one another variable to represent whether if married, if not married, unmarried, 0. Okay. So you can have if you include interaction term, then it allows us to have we subdivide the groups. Not necessarily I mean, if we include more than variable, we can subdivide. But if we have we include interaction term, then we can allow the different categories to have different what we call that, to have different intercept again. So in this case, the groups that when all the variable equal to 0 is our different category. So when d1 equal to 0, when d2 equal to 0, so we don't have this. So this is the model for male, unmarried, male who is unmarried. So because both equal to 0, so the intercept equal to this one, slope equal to beta 1. So consider, let's say we have two dummy variables for gender and this one for marital status just now. So we have these two categories only without interaction. So the above model implicitly assume that the differential effect of the gender dummy is constant across the two levels of marital status, and the differential effect of the marital status dummy is constant or the same across the two different genders. That is, if beta 2 equal to the greater than 0, positive, the mean saving is higher for female than male. This is so whether they are married or unmarried. Likewise, if beta 3 positive, the mean saving is higher for married individual than unmarried individual. This is so whether they are male or female. So this assumption may be untenable. Married female may save. So it's possible that there is different behavior between female unmarried and female married. So we can, one way to take or to allow that is by having interaction term. Can a married female may save more than a married male. There may be interaction between the two quality variables. The approach model is as follows. So if we add this, then we can allow the difference between the effects of married for the case of male and female. Because for male, the effects of married just beta 3. Okay, but in the case of female, the effects of married female is beta 3 plus beta 4. So we allows the married female to have different effects as compared to the married male. Okay. So going back to the previous example, this one, if we allow both intercept and slope to be different, then we use this model. Okay, we have that variable and interaction between dummy and the independent variable. Then we estimate the model. So we go back to our model. Just now, this one is I close this one. So we just use the first observation. Just use the first data set. So this one for which one? Oh yeah, for this one. Okay, so this one. The first example, we just allow the intercept to be different. So we just add that variable. Now, in order to allow both intercept and slope, again, so the previous example, the first example, we only allow intercept to be different, the slope to be the same, beta 1. This one beta 1, this one beta 1. But second example now, we allow both intercept to be different as well as slope. So the slope for this one, intercept for male, intercept for male, intercept for female. The slope for male, the slope for female. In order to have this, we need to add interaction term between dummy and income variable. So we have to re-estimate the model, re-estimate and add interaction y and d1.
这个按一下这个，然后再按星模。
这个是成的。我还行。
Okay, so now so in our model we have saving as the already independent variable, and then C for the beta 0 constant, B for the intercept. We call that the common intercept one B, C for the beta 0, and then we have the independent variable Y income, and then we have D1 to represent dummy variable for female. This allows us to have different intercept. And then, in order to have different slope, then we add interaction term between income and the dummy variable. Okay, and just press OK, so you get the estimate. So you see that before this we get insignificant, but now it becomes significant when we include. When we allow the intercept and slope to be different. Now both intercept and slope both are significantly different for the two categories, male and female. Okay. So now to perform our testing, although we have the estimate here, so we need to perform our testing in order to say from the aspect of from the statistical point of view whether it is safe for us to say there is significant difference or not. Okay. So we have for the case of joint Howell testing, you can perform the test jointly for both intercept and slope. Okay. This one you can perform the joint Howell testing in order to see or to conclude whether the intercept and slope for two categories are the same or not. If they are the same, then beta 2 must be 0, beta 3 also must be 0 lah. If beta 2 0, then they have the same intercept. Male and female to have the same intercept. If beta 3 0, then female and male are having the same slope, which is beta 1. So we need to test beta 2 and beta 3. So you can perform the test whether you perform the joint Howell testing on both coefficient, or you perform the test separately one by one, individual Howell testing. So if you want to perform the joint Howell testing, you have to test beta 2 equal to beta 3 equal to 0, both equal to 0. Beta 2 0, beta 3 0. Okay. So that can be done by using the walk test that you learned before. Okay, you can use the walk test. If you perform the test manually, then you have to estimate full model and a restricted model, get SSE, and then calculate. Again, you calculate and get the test statistic compared to the critical from table. So in this case, this test statistic it is greater, so slightly greater than the critical value from table, and then we reject. Reject meaning that when we reject, we can conclude at least one of these not equal to 0, but we don't know whether both equal to 0 or only one of them. Or if even one of them, we don't know which one, we can only conclude at least one of them not equal to 0. So for this manual approach or manual calculation, that I leave it to you to do later. So you need to estimate full model that has all that variable, and then if the variable, if the coefficient equal to, if the number is true, then this one 0, this one 0, so this is our registered model, and you have to estimate this model without the variable, and then you get SSE for the registered model, and then you can calculate. Okay. For the full model just now, SSE is given here 4127. 4127 is one for the full model. So for the case of restricted model, you have to exclude. You have to remove this D1 and interaction, and then you take the SSE, the sum square of residual. Okay. Now in use, you can perform the test easily using the walk test. You need to test whether the coefficient beta 2 and beta 3 equal to 0, jointly equal to 0 or not. So you just go to view, coefficient analytic, walk test, just like the question last week, right? So the first part, very easy, very easy question. The second part a bit difficult, but the first part, I think all are simple, easy question. I haven't marked the answer now. Okay. So this one, we need to test the coefficient for beta 2 and beta 3. So coefficient number 3 and 4, right? Based on the order, coefficient number 3 and 4. So coefficient number 3 and 4 equal to 0. So this one you cannot use the F test. You cannot use this p-value, because this value is test for all slope. Okay, this one is test for all slope, including for this one, beta 1 as well. Okay. So last week, I think one of the questions asked you to perform the test, you can just take from here. Okay, one of the question to part. So for this example, if you want to know whether intercept and slope are jointly equal to 0 or not, you can perform it like this, and then just okay. So you get the result, test statistic and p-value. So p-value is 0.04, smaller than 0.05. So you reject. The analysis conclude that at least whether intercept or slope are not the same for the two categories, male and female. Whether either one or both are different. And then, because we reject, so we want to know which one, so you can now perform the test individually. You can perform the test individually for beta 2 and beta 3, but this one you can just perform the test based on the t-test. Okay. The t-test, you can just look at the result. You can result estimate. The estimate result for this one, for individual test, you can just look at this one, p-value. So for beta 2, beta 2 p-value 0.0178. This one smaller than 0.05, so you reject. And then you conclude, you reject and you conclude that beta 2 not equal to 0. Okay. But this one, if you perform the test, you calculate the ratio, you divide the estimate minus 0 divided by standard error. So you get negative 2.4, you compare to the value from table, but it produces the same result. So reject and conclude there is significant difference in the intercept for male and female. And then for the case of slope, you can do the same. So but we test for beta 3. So if you calculate the T ratio 2.5, we compare the K value from the table 2.02, so this one greater, so reject. Make the conclusion. Or based on the P value, it is also the same, 0.013, smaller than 0.05, so we reject. Okay, reject the now hypothesis. Alright, so suggestion for selecting the reference category, it should have ample number of cases. Okay, so reference category, which one should be used as reference category? Reference category, the one that the category that we do not include, the category that we do not assign dummy variables. Just now, male and female, we just include dummy variable for female, right? We exclude for male. So male, our reference category for this, the example that we considered just now. So this is just suggestion. It's not compulsory, but suggestion on how to choose which category should be used. Should be used as your reference category. So meaning that the category that you should not include the dummy variable. Okay. So you should have an ample number of cases. The model category is often a good choice. So let's say model category means that which category has higher observations. So just now, let's say you have 49 observations. Number of male are higher than number of female, and then you use male as your reference category. Yeah. I don't remember this one. For this example, whether we have male or female has higher observation. But this example, okay, that's the what we call one suggestion how to choose. And then if there is some underlying or inequality in the category, select the highest or lowest category. So just now, for example, I give you an example about the highest education level. Let's say primary school, secondary school, tertiary school. So you have 3. That's an ordinal. That's already ordinal because the lowest one is the primary school. The middle one, secondary school. The highest one, tertiary education. Tertiary. So that's ordinal. It has some kind of ordinality. So in that case, you can select either the lowest one or the highest one as to be your reference category. Whether the primary school to be a secondary or the tertiary level as your reference category. So you have 3 categories, you only include 2 dummy variables, you exclude 1. So which one exclude? Based on this suggestion, you exclude whether the lowest category or the highest. So let's say you select the lowest one, the primary school, that's you just include that variable for the secondary school and the tertiary education. Okay. Dummy variable trap. If an intercept is included in the model and if a quality variable has n categories, then introduce only n minus 1 dummy variable. So do not include all dummy variable for all categories. Later when we do exercise, then I will show that it is possible to include all categories, but you have to exclude the constant. Okay. So why we have the problem? So for example, gender has only 2 categories, hence we introduce only 1 dummy variable for gender. If we not follow this rule, we will fall into what is called the dummy variable trap. So what is dummy variable trap? The situation of perfect collinearity. So if you go back to the, I think second lecture, I provide this summary of the question in. So the earlier notes also explain about linear dependency between independent variables. You cannot have linear dependency. Remember that I explained earlier in the first lecture. We cannot have linear dependence between different columns of the X matrix. Our X matrix, you express your X in metric form. You have X matrix, which is the first column all equal to 1, and followed by our independent variables. So we cannot have linear dependence between. Otherwise, we have the problem. Otherwise we have the problems of collinearity, so multi-collinearity, the one that we discussed earlier. Whether it's perfect or imperfect. If the linear dependence is exact, then that's what we call perfect collinearity. So for the case of dummy variable, imagine that let's say just now we have 2 categories, male and female. What happens if you include both dummy variable in your model? So the sum of the 2 dummies, this dummy variable for male plus dummy variable for female, then we have all equal to 1, right? Because this one plus this one, then either 1 or 0. So if we take sum of them, then we have a column. We have all equal to 1. So you notice that this one, the sum of the all dummy variable is equal to the first column. The first column equal to 1 because what? The first column represent this one for the intercept, right? We have 1 because we have intercept here, we have bigger 0. So the first column in our X matrix equal to 1. So you have 2 dummy variables, let's say D1, D2. You take sum, dummy variable for female, dummy variable for male. You take sum of these 2, you get equal to this one. So you have perfect collinearity. Okay. So when we have perfect collinearity, we cannot get estimate. So we cannot get estimate. So there is no the inverse of the X matrix does not exist. So that's why if you want to include that variable, you cannot include that variable for all categories. As if you have this one, if you have beta 0, you cannot include that variable for all categories. If you want to include that variable for all categories, then you have to take out this one. Yeah. If you take out your intercept, if you take out the normal intercept beta 0, then okay lah, because you don't have this, you don't have the first column. You don't have the first column. So even though the sum of all dummy equal to 1, then it's not equal to this one. Yeah. But the normal practice we keep the intercept. We keep intercept, but we only include the variable, we exclude 1 category. Okay, we exclude one category. Okay, that's what we call as dummy variable trap. Because the first column equal to the sum of all dummy variables. The sum of dummy variable for all categories. Not all dummy variable, but the sum of dummy variable for all categories. Okay. So if you have 3 different categories, let's say just now you have for education level for primary school, secondary school, tertiary school. So we exclude 1. So that sum of them not all equal to 1. Okay. imagine let's say you have another variable, primary school, secondary school, and then tertiary. You have three categories of education level. So for each of these, for each observation, only one out of three equal one. The other two must be zero, right? Okay, you cannot have highest education level cannot have more than one, either one. Okay, so some of them equal to one, but if you exclude one, then some of them equal to one, but some equal to zero, because you understand? Because let's say because the sum of all variables is three dummy variables. So you have three variables, you exclude one, so that the sum of the two, only two, just take sum of the two, it's not all equal to zero. Not all equal to one, not all equal to one, because some of them must be zero lah. Okay. But you need to make sure lah. If you have that kind of data, if you have three categories, but the third categories, there is no observation belong to third categories, then you still have a problem lah. Understand that? You create that variable, but your data only belong to the first two categories. The third one, there is no any of them belong to third categories. You still have a problem lah. Okay, even you exclude the third one, because so you have to find a way. Maybe you exclude. In that case, you only have two categories lah actually, because the third one you don't have observation belong to the third category. Okay, so remember that one. So you have normally we exclude one. You have three categories, then you just include two dummy. You have five categories, just include four dummy for four categories. Okay, dummy variable for four categories only, exclude one. Okay, now this dummy variable can also be used to perform stability test, the child test that we discussed earlier. But the problem with child test, it only allows us to say whether parameters are stable or not for two different periods. But it does not tell us which one not stable, whether intercept or slope. Remember, that one lecture 2, lecture 3. Child test. So recall that what we discussed earlier, we can use child test to test whether parameters stable or not for two different periods. Okay, so let's say for the given example, we want to see whether the parameter the same, still stable. Stable means the same, nah? Okay, or not stable, meaning that the parameter no longer the same for the period before 1976 and before 1977 and after 1976. Okay, the two different periods. So we perform a test using a child test, but we, in terms of the conclusion, we can only conclude after if we reject. If we reject, we can only conclude that the parameters no longer stable, not stable for the two different periods, which suggests that we need to estimate the model separately. Okay, we cannot just use the whole entire data set to estimate the model, because the result suggests that parameters not stable for the two different part of the data. But we do not know which one not stable, because this one, you look at the hypothesis testing, the null hypothesis, whether we are testing whether the intercept as well as slope, intercept and slope the same or not the same. If we reject the null hypothesis, we conclude that at least one of them not the same for the period before and after. But we do not know which one. We do not know whether the intercept or slope. Yeah, we do not know intercept or slope is the one that's not stable or both. The child test, we can only say that whether parameters still stable or not, same or not before and after, but we don't know which one. We do not know which one. So as alternative, we can use dummy variable approach. Okay, we can perform the same test, we can obtain the same result, but using the dummy variable approach also allows us to identify which one is not the same. If intercept or the slope, if the slope, which one? The slope for x1 or x2 or x3 or x4. Okay, So you open the same data that we used before, stability test. So recall how we performed the test before. So we estimate model first. So we estimate model as usual. So we have y space c space x1, x2, x3, x4. So now for the stability test, it's just like we are having two groups now. Just like male and female, but now this one, the first group is the period before the 1977, and then the second category, the second group is the period after. So it's just like we have two categories, huh? Just like we have two categories. So before and after. Okay. So now, if we just to refresh what we did before, we estimate model, and to perform the child test, we go to view, stability test, the child breakpoint. We just put. So some of you asked me through email. So how to decide this one, the breakpoint dates? It is the first point in the second subsample. The first point, second subsample. In our case, second subsample is starting from 1967, right? 1967. After 1976, so second. So the question says after, or information says after 1976, so starting from 1977. Right. So you have to carefully read this one, the given information. So after 1977, meaning that second period starting from 1977, after 1976. So your breakpoint date starting from 1977. The first point of the second subsample. So we get this result. So what we conclude before? So we get p value 0.01. We reject. We conclude that parameter not stable, meaning that parameter not stable, meaning that whether in the set not the same, or slope not the same before and after, or both not the same. So but we don't know which one. That's the child test. But now we can use dummy variable approach in order to help us to identify. Okay. So what you need to do, you need to estimate a model that allows us to differentiate the intercept and the slope as well. So remember, this is our model. In order to allow intercept to be different before and after, we need to create dummy variable for that period, two period before and after. Okay, now before that we need to create dummy variable before and after 1977. That can be done. You go to quick generate series. Quick generate series. Then you can create dummy variable. Let's say D1 equal. Because we have year annual data, so year greater 1976. No, sorry, 1996. So if we create dummy variable, we assign 1 for the period starting from 1977. Okay, you can see now. So D1 equal. Then you generate series and then you type this. D1 equal at year greater 1976. Okay, then just okay. So you have the design variable. You see that the period before all 0 and then starting from 1997 equal to 1. Design variable. What that mean? So we go back to our model just now. In order to allow the intercept to be different, we need to add the diameter variable itself. So D1. Okay, but this only allow the intercept to be different before and after the two groups. We need to allow the intercept, the slope to be different as well. So the slope for beta 1, for x1, x2, x3, and x4. So we need to have interaction between the mean and each of the independent variable. So we have x1, d1, space x2 star d1 x3 star d1 sorry, this one is the x3 yeah. And then x4. So you add d1 and then space interaction x1 star d1 x2 star d1 x3 star d1 x4 star d1. Okay. Okay. So now you can perform the same test in order to get the same test, the result, just like the Chow test. How to perform the test equivalent to Chow test? You have to test this one. You have to test the coefficient for the dummy and then coefficient for the interaction. Okay, just like what we discussed just now. So you need to test whether all this equal to 0 or not. Okay, then you should be able to get the same result just like the Chow test. So this one, coefficient number. So 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10. 6 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So view, coefficient analytic, walk test. Coefficient number 6 to 10. So all equal to 0. Coefficient number 6, 7, 8, 9, 10, all equal to 0. So that represents coefficient, the additional part of the intercept as well as additional part of the slope coefficient for all independent variable x1, x2, x3, x4. Okay, so you get the same, you notice that you get the same result just like the Chow test. Okay, the test is exactly the same, the value also the same. But if you use the variable approach, then you can go to the next step to identify which one is not stable. Okay, but remember that F test and the individual test is not necessarily the same. It's not always produce the consistent result. Okay, you found at the same significant level. You go back to estimate, you can check lah one by one. So the additional for the intercept, this one for the intercept, remember? The one for the intercept, the additional part of the intercept. Okay, the additional part of the intercept, whether significantly different from 0 or not. So p value greater than 0.05, not significant. So we can say the intercept are just the same before and after. Understand? Intercept just the same before and after. For the case of independent variable, this one, the slope, additional part of the slope for x1 also not significant at 10%. So this one not significant, not only this one, but this one not significant at 5%, but significant at 10. Okay. If you use 5%, meaning that you get different conclusion, conflicting result between f and the t-test. But at least this one almost significant at 5%, not significant at 5%, but almost significant. Okay. But so they want to say, if let's say based on the child test just now, it says that at least the parameter is not stable, but which one? Based on this result, at least we can say that the slope for the x2 is almost not significant, almost significant at 5%. But at least we know lah. I mean, we get some idea that maybe the most unstable, the most what we call the parameter that's not stable before and after is the coefficient for the slope for beta 2. Sorry, the slope for the x2. Okay, slope for the x2. Okay. So if from the test has 10%, then we can say that 10%. If 10%, then it is significantly different from 0. But if 5% is not, because just greater is slightly greater than 5%, 0.05. Okay, so I think we take half an hour break after.